Hello, everyone. Welcome to Lecture 9 of Lean for Scientists and Engineers. We are continuing to talk about how to do writing executable programs in Lean. That's where today is going to start connecting a lot more with our overall strategy has been to start with logic and proofs for scientists and engineers. And now for the last couple weeks, we are on functional programming in Lean. While doing the content for this week, we might actually finish it all today. So we'll see how far we get. And we might not be meeting tomorrow if we get through all of this today, but we will see how that goes. So we're going to start as usual with a recap. And you can see there's lots of items to get to. We'll see what we do, but essentially we're going to continue on with programming. So we will have discussion of lists, a lot more on that after we lightly introduced lists last time. We'll also touch on vectors and then get to some more programming type stuff. Strings, input, output, and this is heavily drawing from Functional Programming in Lean, which is a textbook written by David Christensen, very helpful for us in navigating these things. And we have a CSV parser because that's important if we're going to be able to import data into Lean and do stuff with it. So we keep coming back to this, but this is a foundational part of what we envision for this, is that we have, in a realm of pure mathematics, an ability to check the syntax of code and be sure that statements that we're writing in pure mathematics are logically valid. But in the practice of scientific computing, we then have theories about science. And so this might be Newton's equation of motion, there might be any kind of theory in physics or chemistry or so forth that ultimately form these symbolic models, which we form out of pure mathematics. And we can't always compute things with those. Like we might have things like real numbers, or something might be defined in terms of integration, which you can't always do analytically. And so we have things like approximations and ways to turn these into computable models, which is the basis for writing scientific software. This is then going to be written in code, and you do a simulation. You predict the weather tomorrow, you predict the properties of some molecule or material, and then ultimately compare it to reality. And traditionally, all of this stuff is done by hand as you derive a new theory or prove a new mathematical statement. And then humans will then write code for software as best as they can, and then check whether that code and the model itself, the scientific model, essentially comports with reality in some way. And we are trying to represent all of these things in Lean and validate the construction of math, scientific models, and software all in one system. We had more to say about the details and our perspective on that in previous lectures. We've also previously mentioned we're going to get to this at our next lecture, first lecture of next week. We're going to walk through our progress on this project. But the idea is you can do calculations with floating point numbers. You can't really do proofs with floating point numbers. So you can do proofs with real numbers. And it was last lecture that we really talked about polymorphism and what that means in terms of allowing a function to have defined behavior while it takes on different types. And so if the function is taking a floating point number, you can use it to do calculations. If instead it is taking a real number, then you can write proofs about it. And we had a really nice illustration last time if you want to go back and catch that up. So we've also been talking about programming paradigms. Lean is a purely functional programming language. Most programming languages are imperative, Python, C, and so forth, that you follow a sequence of procedural steps to achieve a result. While a functional programming is more in a declarative style, you define a function. It's more about what it is as opposed to saying what it does. Last time we talked a lot more about functions being a mapping from a domain to a codomain in the mathematical sense. And that continues to be quite relevant. There's also the I say it doesn't let you use imperative techniques. There's caveats around that. Yes, you can actually write imperative-like code in Lean, and today is the first time we're really going to get into that because there are certain things you actually just can't do in a purely functional perspective, and we'll talk about that shortly. What the difference, though, is when you write imperative-style code in Lean 4, you are very intentional about it. You have to add extra keywords. Say, my variable is mutable. My function is partial. I am entering a separate kind of environment in order to write imperative-like code. And we do need that for the stuff we're talking about today, especially with input-output. So a little more background. We talked about mutability. And if you have a matrix of data that if you're using an imperative program and you're just going to store this memory inside of a block in your memory, and then you need to swap out one number for another, that can be done really efficiently with an imperative style. But there's safety drawbacks. You might have a bug introduced into your code. You might make a mistake when you're trying to do this. There might be other parts of the code that can access this object. These are called side effects, and we want to try to avoid side effects. And that's the motivation for in developing functional programming languages. The drawback, though, is this becomes, if you treat this as immutable, then suddenly making this change requires you to copy the entire thing. Even accessing this element requires you to traverse all of the elements from before here. And Lean 4 introduced a functional but in place paradigm. It's not the be-all, end-all of programming language paradigms, but it is a unique thing that Lean 4 brought to the table in ways to manage cost and memory management while maintaining the guarantees that we want. So we also talked about recursive functions that normally scientists and engineers, I don't prioritize teaching recursion to, but this is really important to Lean because we use this for all sorts. We essentially use this to replace loops like for loops and while loops and so forth. So a recursive function is a function that calls itself. So factorial can call itself. And when you give it 5, it can ultimately return 120. This is a non-tail recursive function. And you can instead rewrite this to be tail recursive. And this one prevents this stack of unfinished calculations from stacking up, essentially. And that's a more robust way to handle things than using a for loop. Foundationally, the core motivation to one of the core features of Lean is that you can actually use the mathematical logic of Lean to prove when functions halt. And it's actually the default way that Lean defines functions. So like after I write this function out in Lean, it will on the fly check and make sure that it's satisfying structural recursion so that I know that it's going to guarantee no matter what value of n that gives. And we talked through this idea of, yes, you can use logic to figure out how some programs finish. This is not, this is related to Turing's conception of the halting problem, which you can't necessarily prove whether an arbitrary program written in the language is going to halt or not. That is undecidable, but that doesn't prevent us from proving that some programs halt, and we use that all the time in Lean in order to guarantee its code is correct. And so we'll be talking about this kind of syntax again today. This is a function that takes in natural numbers and outputs natural numbers. And there's a case 0 and a case n+1. And this is doing pattern matching of whatever your input is to the output. And almost finally, we have lists and arrays. And we talked about how lists in Lean are linked lists. Arrays are also in Lean, and we'll see that briefly. A list in Python is actually an array. If you want to implement a linked list in Python, you'll have to do it by hand or import something that's not in regular Python. And some of the differences between these are illustrated here in terms of their pros and cons. And from last time at the very end, we were talking about lists. And so when you declare lists, you need to specify the type of the data included, or you can specify a generic type and use polymorphism. So we illustrated some of those cases. And then finally, we showed that if you combine this idea of a list along with recursion, then we can add up all of the elements of the list. And this is where we stopped. And I wanted to pick up on this because I didn't explain this example as well as I should have. So that is where we're heading off to. Okay, and this time I will have to actually guide you a lot more because I uploaded a whole bunch of files. The file we should go to first is this lecture 9 file. lecture9.lean. Okay. All right. So, the first thing we see is I've defined two lists. I've made them different lengths at this moment. And it's possible to make this, whoopsies. Oh, it doesn't actually. Okay, it fails to synthesize, no. So I can eval list.length and pass in data 1, and I get 7 coming out. So this is a very handy function. So list.length is a function from Lean associated with the type list. And another way to do the same thing, because data 1 is an object of list type, I can alternatively get this by simply calling the length function using this dot notation that's referred to when we often deal with these things in MATLAB. So this is two different ways to access it. I can either apply the function list.length to the list object, or I can just invoke the list object because the list object specifically knows what type it is, then I can go and obtain the length from this. we can index it. So this one actually works very similar to Python. You just define your object and you put in bracket notation and you retrieve the third element. So this retrieves 4 out of here. Again, it's similar to Python. Python indexes from 0, so it's also lean also indexes from 0. So if I want to get the first element of the list, which is a 1, I use the index 0 to get that, and so forth. We can also get the tail. I can go and get the tail. So what tail does is it gets the last element of the list. I apply this on data 1 and I'm like, wait, what? It's returning a list. See that there? It's returning 2, 3, 4, 5, 6, 7. I'm gonna, oh, I should hide I can hide this bottom part a bit more. There we go. I have 1, 2, 3, 4, 5, 6, 7. Okay, that's weird. Why didn't I get the element 7 back? Well, that's because, remember, this is a linked list. And so under the hood, I have defined this list using these elements. But this is actually a list of length 2, basically, where the second element is another list. And the third element, well, it doesn't have a third element, so I go to list of length n minus 1, basically, is the length of the remaining part of my list. Oh, we got a lean. Oh. No, it might not just be you. Here, let me fix that. Thanks for mentioning that. I was noticing an anomaly here. Okay, I got it. Wait, is that right? Let me see. Yes. Okay, let me fix that. Sorry, everyone trying to follow along. I didn't upload the right file. Nope. This doesn't go here. Okay. Lecture 9.lean is now correctly in the Zulip folder. Thank you for chatting that out. Okay. That should help you. I mean, you can follow along by looking, but it's a lot more fun to play with it yourself and look at all the types and things. Okay. All right. And if I want to get the head of this, I actually have to use, I can't just apply head. If I try to apply head on data 1, okay, this function, this expression, data1.head, has an interesting type. It is a type of from data1 is not an empty list. Because I can't go and obtain an element of a list that's empty. So that will be undefined. And lean is really picky about constantly avoiding any functional behavior that will be undefined. And so I didn't actually quite figure out exactly what the exclamation point does. But this is the way you get around that, and you can access it for applying it to a list like this. And so if I, apply it to a list of 1, 2, I get this. But if I apply it to a empty list, then we get a stuck problem, and we get expected type, and it tells me it can't do this operation. It doesn't work type checking wise. Likewise, tail doesn't like it either. It can't handle an empty list. But in this case, if I give it a list of just one element, it will actually return an empty list because of how a list is defined. So I should have included, here, let me pop back to lecture 8. I should have shown my definition of a list here. Where did I do that? I had 2 redundant lists. Went too far. Okay, here we go. This is the primes under 10. I'm just going to move these into let's get this back into lecture 9 lean. Here we go. So if I have a reminder from last time, if we have primes under 10, I can either just say this is a list of 2, 3, 5, 7, but under the hood, it's essentially converting this into the following. I have a list constructor applied to 2 as a function. So this is a function that applies to the number 2 as well as then a list. Or a function, I guess. This is a function that then applies list constructor to 3 and another thing, list constructor to 5 and another thing, and ultimately all the way down to list.nil, the empty list. And that is how this works. And so that's why when I apply tail to a list that only has one element, it returns back the empty list, as we were seeing right here. Let me hide the files. Yep. So like if I apply tail to something with just one element, it returns the empty list, because a list with just one element is a list being constructed of one element as well as the empty list. So grabbing the tail of this returns the empty list. Okay. Yep, and then here, I mean, this is the neat thing that Lean can do. You can prove rigorously that these 2 objects are definitionally equal to each other. Okay, so we also have a little bit of code for slicing a sublist from a list, because, I mean, if I'm familiar with Python, so I might sure like to, do data 1, this type of syntax is one way to pull out elements 2 through 4 from the list and grab those, but this doesn't work. It doesn't understand that syntax, and we looked around, didn't quite see something like that, but we can write our own to do this. And so this is a function, I think Alan wrote this function, for slicing a list, where you have a list. So this is a function that takes in a list, and it takes in a starting point and an endpoint that are both natural numbers. They're typed natural number. Why are the starting point typed as natural numbers and not integers or rationals or anything else? Any ideas? We want these, yep, Simon is right. We want these to be non-negative. Okay, yep, my question is, why are start and end natural numbers? So the way I think of this is these are indices in a list, entries in a list, and they start at 0. You don't have the -5 index of a thing. It just doesn't exist. And so, yeah, we should, the correct type to use here would be a natural number. Because if it would take in like a negative number, then it'd be like, well, what am exactly am I doing with this, for example? All right. When there's some discussion of what to do about infinity in this. Well, so that's this curious thing. We'll talk a little bit later about the difference between vectors and lists. Vectors have a fixed length. Lists don't. Fin indices would be safer. Yeah, because technically I could put in an infinite. Nat is defined. I mean, they're not the extended. Yeah, I mean, nat, yeah, maybe including it as a finite type would take out one edge case there. That's actually a good point. Um, but anyways, this is a bit of code that can do slicing. So I can take data 1 and I can, whoops, and I can do slicing and then pull out a sub part of that list, for example. Here is a way that you can use the list.filter. This returns the elements in the list for which f returns true. So yeah, take a look at this. So we have, it's of type list to list. So it takes in a list and returns a list. And you apply your list on, you apply filter on a function or f is a Boolean. Yep. And then for which the element is in the list is true. And we can do that by defining a Boolean thing. So my first attempt at this was actually with a proposition, because I can define a proposition as x is greater than 4. But that's not actually the type that filter is expecting. The filter type is expecting Boolean. So we need to use a Boolean type. And now I have a constraint that x must be greater than 4. And so I can apply that constraint to data 1. And you can see the eval comes out as 5, 6, 7 as a filtering on that list. You could turn this into like an evens or odds or something like that too. So here's another way to do this. And this is using an anonymous function. So I glossed over this when we were talking about functions because it's a little bit easier, I think, to visualize. I'm going to define a function outside of my, as a standalone thing in my code, give it a name, and so forth. What an anonymous function is, it's really that. It's a function that doesn't have a name. It's anonymous. And you only really introduce these in order to talk about functions or to introduce a function and use it in a very narrow context and then forget about it, essentially. That's what an anonymous function is for. And here we are going to be creating a Boolean function saying that my function is a function of x, and it returns x is greater than 4, which is coming out of that. And so you can either put this lambda character in there, and lambda is this Greek letter. This goes back to lambda calculus, and it's connected to sort of foundations of functional programming in general. We're not going to spend too much time on it, but just recognize that it's also a sort of synonym in Lean for this fun keyword, which basically starts out what an anonymous function is. And this is the assignment of the content of that function is given here. And essentially then we introduce that function in line with list.filter, so I don't need to define my condition on the outside. That might be useful if I just want to define my filter like this and move on without defining the conditions that it is about. And I already showed slice list. I guess this should go up here. Okay. So that introduces some basics of how to handle lists and deal with those. Last time we talked about how to sum up the elements in a list. And this is setting it up as a recursive function of type list of natural numbers going out to a natural number, because I'm going to output a natural number after adding up all the terms. And the way to walk through this is I'm going to define, if I have an empty list, well, this is going to return 0. If I have a list that is not empty, I'm going to pattern match to this bit of syntax here. And so what is this? I just have a mind blank of what this is particularly called. But this is I think it's the list constructor. But what it's going to be doing is it's going to look at this list and it's going to match two things in it. It's going to say the first element of my list I'm going to assign to the value x, and the rest of my list I'm going to assign to the value x's. And so you can even see that when you put the mouse over. The x is the natural number, and x's is a list of natural numbers. Cons, I guess, is what it's called. Cons. Does it stand for constructor? I think it stands for constructor. That's what I think it means. Yeah. Okay. Thanks for confirming, Simon and David. Okay. So I have done the matching. Ooh, it comes from Lisp. All right. Interesting. So I've done the pattern matching of x and x's, and now I'm going to output something of this. I'm going to output x plus, it's a recursive function. Now I'm going to hit sum of list on x's, but now what I've done is x's is one less long than x was, than the original x. And so now I have list n coming back, and it's one less, so I call the function again, and I keep going and going and going. And a reminder of what that tends to look like when doing a recursive function call. This is what happens when I'm doing factorial. I apply factorial of 5, and I turn it into a call of factorial 4, a call of factorial 3, 2, 1, and 0, and then I return the base case of my recursive function, and I terminate my function. In the sum of the list, I do the same thing, and I will be adding up all the things until I end up with an empty list. I only have one element in x, so I return an empty list as x's. Next time I come through here, I return a 0, and then I add everything up together. A note, this is not tail recursive. So it wouldn't be the most efficient way to do it, but there are tail recursive versions of this in functional programming and Lean that you can learn about how to set that up. Okay. Here is another function applied to lists. So here I'm going to apply the square operation to every element in the list. That means I'm starting with a list and I'm producing a list of natural numbers. In this case, I'm returning an empty list in my base case. And then for my x's, I need to match the first element and the rest of the list. And then I return, check this out, I return a constructor. And I know what this constructor is. The first element is going to be x squared, x times x. And then the second element is square list applied to the rest of the x's. Make sense? I have the rest of the x's is now baked into that second part of this list. How do I keep going? Well, I just return to the function and I keep going until I end up with an empty list. The last step that I will be doing is applying square list to an empty list, and that means I just slide in an empty list. And you can, if you go back and remember what the long form looks like for a list, we would end up with a list.nil. We would have an empty list at the very end of my list, and then all of this would be constructed step by step by squaring all of my numbers. And again, I want to bring up, this is in contrast to imperative style programming. Because in imperative style programming, for example, you might imagine, well, let me start at the first element of my list, square it, and put it back where it was in the memory. Well, halfway through my calculation, I have a list that's halfway squared and halfway not squared. If everything works fine, everything works fine, but it's sort of an unsafe way to do it. You might instead say, I should create a new variable that has all these things. And that is a safer way to do it with fewer side effects. All right, and so you can combine these two ideas. I can do a sum of squares list. And so, this one is very, very similar to just the sum of list. You can see the only little difference is instead of returning x plus it, I'm going to have x times x plus this. I also wrote here, you can also use fold. List.fold L means fold from the left. I thought this was working. What is going on? Or do I change? Well, okay, I forget what I was trying to do with that. There's other ways to do this using methods that are attached to list. Okay, but I'll take that away for now because it's not working. Okay. And that takes us to this one. And so you all have the answer in front of you, essentially, but we're going to build this one on our own here, live in class. How do I get a squared difference? So we do this when we do like regression analysis, or if I'm trying to do, I would do this if I have a prediction and a measurement. Okay, and I want to get what is the squared error here? What is the mean squared error of this? Well, one way to start getting into this is, well, this one's tricky because I have two lists here. So I actually need to define a lot more cases. I need to define what am I going to do when the first list is empty? What am I going to do when the second list is empty? What am I going to do when both of them are empty? And what am I going to do when both of them are occupied? And the way to square the difference between these, okay, I'm going to start with the case of, well, let's say I have one list. Okay, I'm going to call this x1s. And now I'm going to match this with x2. And this is going to map to a new list. Okay, and I want this new list to have, let's do x2 minus x1. And I need to then finish off with square difference applied to the pair of lists, x1s, that's left over. And I think I need to put all of this inside of parentheses. Maybe not. No. Oh, no, this is fine. I'm simply missing cases. No, it's not a problem. Okay. Yeah. So I think this is doing what I want it to do. But it's telling me I'm missing cases. Oh, you're right. I need to square it too. Okay, so I do the difference and I can square it. There we go. Thank you. Okay, but here's the thing, is I'm not done yet. Normally, like in Python, you'd be like, okay, I'm done. I did the work. Okay, but we need to finish all the cases here. So we have one case that's missing where the first one is a list and the second one is empty. And I'm missing a case where the first one is empty and the second one is the underscore means anything that's left over. Okay. So let's do the case where the first one is empty and the second one can be anything. We could define this. I need to return a list. I could define this to return an empty list. Seems like a reasonable thing to do. And I could finally finish with anything and an empty list. Oops. And say, okay, now this is that case. And now I have a function that's finishing. Okay. So I slowed things down to maybe help you see how you think about these things and construct something that's a little bit more non-trivial here. You can actually simplify this because after you've defined one case, you can actually use underscores to fill in all of the rest of the things. And I think I don't need this. Yes, so I'm fine. So I can actually just use this in 2 lines. I can say, by the way, I'm defining one thing that I care about, and all the other cases, I'm just going to be returning an empty list. And so finally, after we've done all this stuff, what is the squared error? So the squared error of something is when I have 2 different lists and I want to calculate their difference. I want to square all of their differences, and then I want to add them all up. If I want the sum of the, I think this would be SSE. Yeah, the sum of the squared error. Not a SSE. There we go. And so the type that I know I want this to have is it should be taking in 2 different lists. So this is taking in list 1, L1 and L2, and these are going to be natural numbers in this case. And I want to return a natural number. And now I could go and write code by hand, but the really nice thing is I can actually construct this out of the functions we've written already. So the first function we need to do is we need to get the squared difference. So if I did square difference and I applied it to L1 and L2, okay, well now I have something that should be evaluating to a list that I now need to add all together. And so to do that, I have a list, so I can go and get the sum of my list, sum list up here, and I can add all of these together. So I can do sum list of this. It's not quite working because we need to do order of operations. So by putting this in parentheses, then we get this to type check just fine. And we can run an eval. We can say that, so my sum of squared errors between these is giving me my data. And I want to just think, I'm wondering about anyways. Okay. So, but notice what happened here. Remember at the very beginning, data 1 and data 2 have different lengths. And that's kind of weird because normally we say, oh, if you have two data sets with different lengths, it's not meaningful to talk about a difference. You don't say I have a two-dimensional vector and this is how far away it is or how different it is from a three-dimensional vector. That's a weird type of question. And nonetheless, we didn't get a problem, but it's because we defined the behavior of our things in this way, that when one of these is an empty list and the other one is not an empty list, we're just going to ignore it altogether. And so if I, for example, take off the seventh element, then we don't get any change in our answer because it's just dropping it after all. If I put the seventh element back in and I take off the 4 of this element, well, then we are going to get a different result because now we're adding up. Now we're operating. We'll be chopping off the top 2, and this is not giving me what I was expecting. But I think it's because of finicky things around that power operation of subtraction. Not subtraction is going to round that down to 0, and it's not going to contribute. I think we wanted anyways. For the sake of argument, I'm going to go back to what I had before and I did some squares list. Oh, yeah, which wasn't actually right. Okay, so the new version is correct. I'm glad I retyped that by myself because this version has the right meaning. If you check this math in Python or something like that, you'll get a different answer than 72. And that comes back to this concept of junk values that we talked about. So when I do natural number subtraction, this operator saturates at 0. So some of the elements in data 2 are larger than elements in data 1. And you end up with a smaller number minus this one, which returns a 0, instead of some negative number. So it is working as I defined it to work, but there's something unexpected happening because of the way these be natural numbers. If I had all of these be integers, for example, then we wouldn't have any issues squaring, we would do the subtraction and we would end up with a negative number instead of 0. And then squaring it would give the SSE that we would be familiar with. But even that, like most of the time when you're calculating a difference thing, the type you should be worried about is float, probably. And that's something that you can do with polymorphism, which we talked about last time. So a very brief note about matrix. So I've defined a matrix here. This is a list of lists. So not too complicated. Okay. You can also do lists of strings, for example. You can do, these are, Oscar wrote this code. You can have Oscar, Boolean, float, true, false. These are just strings, essentially. And so you can have a list of string objects. And we can apply filtering to these in order to pull out. This is the fifth element of that list. Here, not actually the best example. I should have trimmed the filtering out. Oh, no. This is, okay. What filtering is doing, this one is checking out the minimum length, now I recall. So the minimum length here is being defined as 5. So I want to pull out, I want to filter out everything that is 5 characters or less. And this uses a lambda function and obtains the length of my list and checks whether it's greater than the minimum length. And this is how we apply this. This uses some IO stuff. I'm going to talk about that later. Okay. And that brings me to wrap up an introduction. A lot more detail on lists and how to work with them and how to access them and manipulate them. Okay. So let's move on to vectors. And after we've talked about lists here, we're set up to talk about and Simon has some suggestions using zip with and point/element-wise functions. I concur. Yeah, use built-in things whenever you can. Thank you. All right, so on to vectors. We had a problem in that previous thing. I was doing a sum of squared errors calculation, and my lists had different lengths. And that led to some weird, unexpected behavior where it's actually giving me an answer when I would like it to ideally stop and prevent me from doing that. So vectors are a type that bundles a list along with the length of this list as a value. And this is possible. This is not possible in programming languages that are not dependently typed. I mean, you can define an object and you can go and calculate things about that, but the type of that object doesn't intrinsically have those values attached to them. That's possible when you have dependent types. And that's something that a vector is. And the vector type depends on this value. And so this is the syntax for vector, where you say, I'm going to have, what is alpha? Alpha can be any type. This could be a vector of strings, of natural numbers, of integers, and so forth. And so this is the type of the contents of your list, the contents of your vector. Then you have a natural number for n. And just as we mentioned a little bit ago, n is the index, essentially. It's associated with the, I shouldn't say index, it's the length of the list. And so since it's always going to be some natural number, it won't be 0 or larger than that, then we end up with this being defined as the type. These curly braces allow a more complex type to be expressed. And the vector is going to be for some variable L, which is a list of this type alpha, having a subtype of this length of this list being equal to the natural number. And we'll open that up in Lean right now. So you can actually pop, if you went to the MATLAB documentation, you would find this is how vector is defined in MATLAB. If you put your cursor over vector, you can see this as of, it's a type. Vector itself is a type, and it takes in a type and a natural number. And so you need to provide both of those things when you define what vector is. Then we have this slash slash, which is how subtypes are written. And so you can read in the documentation string. So subtype, usually written as x of type A slash slash p of x, where the elements of this left-hand side type, are defined for which p of x is true. And so that's what you can see. There's, essentially this L dot length is a proposition. And this is, so you can think of, there are tons of lists, and they all have different lengths. But this only includes, this type only represents the lists that have length n. And that constrains it and makes it helpful. And so this is a proposition there. And that's sort of how to unpack and read in what is going on here with this vector type. I can define an example vector. Let's do this one first. Thanks to David, by the way, for this example. So I can have an example vector that I'm going to be defining. And you can see the way I write the type is going to be vector of type natural numbers with length 3. And so we then define this equal to be, so we have a list followed by a tactic, a proof that returns true for this case. And we can use a simple one because the length of this particular length is equal to 3. But you'll see I run into problems if I want to make this longer. Okay, now I say I have this tactic is not true anymore. Reflect does not prove that my list has length 3. And that's one way we can actually build safety into these systems. So if I wanted to access, if I had some code and I ended up needing to grab the 5th element out of that code, well, it's how can I prove that it has that 5th element before I try to do that? That's what this type of procedure, this type of syntax can be used to do. The other thing that ends up just being handy is, I believe this makes execution easier too, because you tell it in advance how large the vector is going to be, and that enables you to do things in a more general way. You can prove some more things about this. So here's a way you can obtain the sum of a vector. So I'm going to I want to have a function that takes in the number of elements that it has alongside the length of the vector, the vector itself, and returns a natural number. And this will return, it goes into V. V is the vector, and we can attach a method to it to go and get the values of the vector. Here. So let me show a little bit more of what's going on. So we have an example vector, so we can eval example vector dot val, for example, and you can see what this val has done is it's stripped out the proof part of it. It stripped out this proposition about the length, and val is just retrieving the length, the list itself. I can put my cursor over this and see it's type list that we've been seeing before. Okay. And now, since I have a list, I can just do sum over it. I know we had our fancy fun little functions up there, but yeah, you can sum over a list of natural numbers using just the sum function in Lean, and that's what this is doing. So this is doing a sum of for a vector, essentially. And now I can eval sum vector. I can pass in the number of elements it has, and then I can give it the example vector, and we're good to go. We use the length 3. So you could even do example vector dot length, for example. Nope. Oh, I can't do example vector dot val dot length would, because this would be the values of that list, and I can use length to get that list, and that would pull out example vector here. I wonder, I wonder if we could even take out the length call out of this function altogether. Maybe not, maybe. But actually, I think that's what just eval would do. Oh yeah, we wouldn't, for this particular simple case, I wouldn't actually need to do that thing. I can just do example vector dot val dot sum, but you're writing your own functions. Maybe they're not built into MATLAB already, and the methods that are developed about it, so it's good to know how to build these on your own. All right, and that's all I had on vectors. Okay. We tried for a little while, but we didn't actually quite figure out how to set up the imports, so we can just use vectors naturally out of MATLAB, which is a little frustrating, but can chat about that in Zulip if anybody knows how to do that. Bottom line, the reason we like vectors is because, let me get into MATLAB 4. If I go to MATLAB, we have proofs. We have definitions. We have all this math available to us about vectors. And that you can use those. You can draw on those. If you want to do math with vectors, if you want to derive theories about vector math and lean on the things that are part of MATLAB vectors already, you can go and get those kinds of things. But today I didn't quite have that part of the example ready. Okay, so we're going to leave that file behind and move on to strings. So the main thing I really want to point out before we get to our string examples.lean is Double quotations define strings in Lean. Single quotations define characters. So Python, for example, both of these will, they can be used interchangeably for strings. In Lean, you got to be particular about it. Okay. Okay. Thanks to Kevin for writing up a ton of examples of ways to use some of Lean's built-in string stuff. I mainly show these because, again, we're talking about programming and we need to print stuff all the time. We're not just doing math, but we're working with things that have names. We want to write sentences, describe things about that. And for the most part, I'm going to try to somewhat quickly go through all these little examples. But if you want to do something with strings, then look at the documentation, figure it out, ask Zulip, ask ChatGPT and things like that to help you figure out how to do those things. Lean is a much newer programming language that doesn't have as much developed as things like, as more mainstream programming languages. So the library of commands and operations you can do with strings in, for example, Python is much larger than what you can do in Lean. If you can't do something then and you really think it would be good to have code for that, well, then build it and submit it as a pull request to mathlib or the standard library of Lean, for example, and build more tools so other people who want to do the thing that you needed to do with your strings can use that instead of writing their own. So here's a string example, and we have seen some of these before. We defined strings for when we were talking about structures with the atomic elements. But a character is defined using single quotations. And if I apply string example, dot toList takes in a string and produces a list of characters. So I can turn hello as a string into a list of characters. I can go backwards. I can start with a list of characters and turn that into a string. Look at how specific that is. This is as string is only defined when the type is list of characters. We have ends with. We have does this end with 0? True. We have trim. This takes in hello. I added some extra spaces. Then I did a dot trim. This trims out the white space characters. We can turn it into capital letters to upper. Plus performs string concatenation. What does plus do? Plus is not defined, but plus is defined for strings. And that means combine string example, which is hello, with space everyone, a string that comes after, and that combines them into one string. If I have some value, for example, I can use X exclamation point followed by the double quotes in order to insert something into here. So string example, I have defined already, and that is equal to hello. And that's why we get hello everyone from doing this. Here I'm just inserting it into this. I could do more ways of doing that. I just want to check. Can I do it twice? Yes, I can. Yep. So if you do this S exclamation point, it substitutes it as many times as you have that expression in there. To reverse a string, you need to chain string methods together. And so this is a way. So we start with string example, then we apply to list, and we turn the string example into characters. Then we apply reverse. Reverse just takes a list. It doesn't take a string, but it reverses the elements in the list. As string goes back and turns the list that came out of reverse into a string again. And so on. Yep, and so applying that gives us hello backwards. All right, so the next thing gets really important because this involves turning strings into math. And you'll see in a minute why that's quite relevant. Well, yeah, no, I'll share that shortly. Okay, and you can turn a string into a nat by using toNat exclamation point. And this one interprets the string as the decimal representation of a natural number. So I can, if I'm defining 1, 2, I can go and extract 12 as a natural number that comes out of this. All right, and then this is what Kevin wrote to do some float parsing. It's just what we could find. I think there's something in the of scientific part of float that is more comprehensive than this. This one successfully turns this float into a, this string into a float. It doesn't, however, work for scientific notation. It doesn't have an idea of how to deal with, for example, a letter and a negative value inside of this. Any questions about strings? Don't worry about all of this too much. I'm just illustrating a thing. You can unpack it on your own. Self-study there. Okay. Time to talk about input-output. So in David Christensen's Functional Programming Lean, he has this really helpful analogy of how lean interfaces with the real world. And it's the idea of a restaurant where you have the front of house, or the dining room essentially, and then you have the back of house, the kitchen. And people on the wait staff, they will go out into the dining room and they'll take orders. And so order your coffee, order your sandwiches and so forth. You take that note down and then you bring a message to the kitchen and you say, hey, we have some request, we have some message. And then you give that to the back of the house and they prepare the food. Then they send back the food to the waiter who takes it back to the dining room. And there's an analogy between this and how lean works. Because out in the real world is messy, unpredictable. In the realm of mathematics, we have pure functions. We have MathLib. All this stuff we know is confidently true about mathematics. We have the verified logical syntax. I have a list and I know, I'm doing a summation over the elements of the list and I know it's going to terminate. Lean has a guarantee that no matter what list I give it, I will actually terminate in the end. And that's pretty powerful and cool, but I've been talking about this big gap between these worlds, that interfacing code with reality is it's just tough, and it's like, how exactly am I going to, that's why we have bugs happening so often in other programming languages. And Lean is not immune from this because there is just a mismatch between, there can be mismatches between what is out there in reality. You can't anticipate every possible thing that happens in reality. One example is, so you think, maybe in reality, I'm going to send a list into my Lean code. And so the Lean code starts seeing this list, and I was like, I'm going to add up these elements. And so it starts adding up the elements. Well, what if the list of numbers is infinite? Now I can't prove what I was intending to prove about it anymore. The list goes on forever and ever. Or what if halfway through this list that's coming in, I decided to change the type of the stuff, of the stream of text that's coming in? Things like that. And what bridges this is called the I/O monad. And monad is a technical term. I'll talk about it just briefly here, but I've shared some links in the slides for you to dig more deeply if you want to get into monads. We're going to treat those really lightly today. But the general idea is we need something different for Lean. And we need to define something specifically as input-output. We can't use the normal things. And this ties back to the differences between imperative and functional programming. This is where Lean does actually let you use imperative techniques, but this is just about the only place, essentially, because you need to, you can't define a function with respect to the real world, because the real world is undefined, essentially. Like there's no way to map everything in the real world to something in Lean at least in an interesting and meaningful way. So functional programming in Lean, chapter 2, is a great place to learn more about how input and output works. And that's what I will be sharing from today, is these illustrations. And this is why we actually have to have so many different Lean files in the exercises today, because in the Lean code, because every time you do input output, you kind of need to be running these in separate files. So here's your hello world script. It's a single line of code. Save it as hello Lean, and then from the terminal you run it like this. So let's go and do just that. Here's my hello.lean. Okay. I renamed my folder again. All right. Lecture 9. Oh. Okay, so you do lean -- run hello.lean. And here's our hello world. We'll be using this more. I'm going to make it a little bigger. Okay, so now we see our hello world coming out of this. Great. Now, what is it doing? So we can see in the center we have this assignment operation. Main is the name of our definition. This is not actually a function because it doesn't come from anything. We're just defining the output of this. And the type is IO unit. Unit is a canonical type with just one element. It's a super simple type. It's used in order to return nothing, essentially. So if there's, in other programming languages, you might return a void in C++, or a void function in Python, for example. You can just say, I'm not taking any arguments into my function. this is how you set that up here. And then we have this IO print ln function, which takes in a string and prints the string. So print ln means print the text and also add a new line character to the end of that. So we'll something if you're printing something and you don't want the new line character, you can take off ln. If you do want the new line character, then you can leave it in. All right, I'm just going to make sure I didn't miss anything here. Yep, okay. So here is a more elaborate idea that allows us to do input and output. So let's do lean -- run hello name .lean. We have IO print new line. How would you like to be addressed? I can type in my name, and now it fills it in. Okay. But back to what's going on here. This is following do notation. And let me actually pull out. I have a slide on do notation. I should have put that in. Here we go. I should have put that in today's lecture slide. So this is from lecture 8. The idea is lean can express imperative style programming using do notation. However, if you just want to write programs, this makes proofwriting much more difficult. So here's a way to do the factorial function that we talked about before using do notation. You define and you say do, essentially. Here is, I'm defining the what's your name definition, and I'm starting this whole thing with a do block. And what that then allows me to do is it creates this chain, this sequence of expressions, of actions to apply in this order. And so these will run top to bottom and perform the thing that I wanted to do. So there's a couple components to this. The first is this, my slide actually. I'm going to do my slide for this. I like how my slide put this. Okay. So here's the code. We use this left arrow to bind the right hand to the left side of things using a let. And we do that for the standard input. We do it, which is going to essentially be the thing that takes in my input. Then we define the output. And we get the standard input from that. And finally, then we print with a new line, how would you like to be addressed? And then we let a name, and then this one is colon equals. It doesn't involve this backwards arrow. And that's because the right-hand side is purely a function. It doesn't involve any of this weird IO stuff. That's why we need to put these left arrow on here, is because this IO stuff is making it harder for you to do proofs. And then finally, we do this string, this passing a variable into a string where we obtained a value for name and then we passed it into here. And this one again uses IO. So what is happening with all of this IO? Well, here are my comments again. So let introduces a variable that will be assigned as such throughout the do block. The left arrow means the value of the expression is an IO that should be executed. And essentially what this does, this particular line of code is lean looks at the right-hand side and it evaluates what it is. and what its type should be. Once it has learned that it's an IO action, which is this get stdin, it applies that to execute that IO action in order to create this value. And this value has this unusual kind of type. It's an input-output FS stream. Okay, but there's a subtle reason for why this two-step process can be helpful and interesting. The same thing is happening here, with some differences. In this case, we have this IOFS stream. We're going to get line out of that, execute that IO to create this value input, and input now has type string, and string is nice because string does not have type IO. So we can do pure function application with input now. We can't do pure function application with these because they're IO and we can't guarantee what's going to happen. And so we have the structure of the input prompt in this way. So let's explore that in Lean with the handy mouse over. And these are in right here. Ooh, in one line, could we get let input goes to io.getSt? Well, we can certainly try it. I tried a few things. I wanted to trim it up. It's already shorter than the version that David Christensen published in his book. He had a let stdin, keep that separately from std out. So you define std out, and then you start mapping std out to the into this string, for example, but it got easier for it to do it this way. Okay, so I was going to try to let, I think it's not going to work, but we can try the code you're suggesting. io.get stdin. So get oh, it's actually the same. We're just taking the right-hand side here. Why do we need to slide across? Oh, that's a really good question. Why does this intermediate thing need to exist in the first place? Because honestly, yes, it's really awkward. Most programming languages don't make you jump through these kinds of hoops. Let me try to bring in the answer to that. I'm going to check to see what my next slides were. Oh, yeah, we'll do that later. Okay. Yeah. So I need to keep Lean open. And I wanted, oh yeah, true. You would add in std dot, I mean, I think it's a little twisted, but we could try std get standard in dot get line. It can't resolve this one. Oh, I would want IO. I want IO dot get, yeah. So the types aren't lining up is the problem. The environment doesn't contain these things is the answer to your question rigorously. But I wanted to, since you asked, I wanted to get programming in Lean over here and look for the language. And look at us, we're right here. Okay. In 2.2 is when he talks about this. And Here it is. Okay. So this is what I just walked through. You first look at the right-hand side. You evaluate the expression to the right of the arrow. Because this is just a variable, you simply get the value. So you get the standard output, and now we have this. And the resulting value, okay, is an IO action. So next we need to execute this action in order to get a value that represents the standard input stream. And the same thing happens. So I just use the print ln instead of creating a standard output thing, which is a short way to do it. And he asks the question, let me find that again. Okay, here we go. Here's your question, I think. And this is what I think really gets at your question. Why is there a distinction between evaluating expressions and executing IO actions? Why not simply carry out the effects during evaluation as is done in other languages? Other languages don't draw a distinction between these things. And the two answers that David Christensen gives, if you separate evaluation from execution, the programs, by doing this specification, you can be explicit about which functions have side effects. We've talked about side effects before. It's easier for me to distinguish which parts of the program are pure functions that I can do proofs about and which are not. And that's specifically the case when I land on here. If I'm looking at the types of these things, input is a string. By the time I land on input into this part of the code, I know that I have a string and I can write proofs about the string. I can do, because it's pure idealized string concept. This is an IO object. And it's a lot harder. You basically can't write proofs about IO actions. And so that separation is helpful. It coaxes the programmer to avoid bugs. The other reason is that not all IO actions need to be executed at the same time when they come into existence. And sometimes it's useful you can do more fancy things with functions. And for the sake of time, I'm going to breeze through these points, but essentially he comes up with this idea of having a separate function that does run actions. So you have an earlier function that creates your actions, and then a separate function that runs the actions. And the one that creates the functions can be pure and verified, for example, I think. While the one that runs it can avoid that. Don't quote me on that last comment. Okay, but yeah, hope that helps. Ooh, and Simon has a suggestion about binding to pipe the IO action into the next action. Oh, interesting. If you have exact syntax, you could share it and we could try it. Okay, but in the meantime, I'm going to start getting into the next part, which is we have input output. Let's do a calculation with this. Let's get a number from standard input and calculate its factorial. But we immediately run into an issue because what happens if the standard input doesn't provide a number? What if you provide a string? What if you provide a floating point number, a negative number, something like that? We need a way to manage error handling. And that's what takes us to the option monad. And here. I'm not going to get too much into this, apart from telling you that IO is a monad, option is a monad, and I have a couple links to teach you more about monads. But like this first one is a dense 20-minute video. He explains it far better than I can. So go ahead and do that. Oh, and thank you. So Alistair came up with a little suggestion on how to one-line that. I like this. We can do this to one-line the input, for example. So there we go. Oh, thanks. That's even cleaner. Now we have changed together these things, but you can see there's stuff going on. You have to manage your order of operations. This might make your code cleaner and shorter, for example, and it might even be more efficient because you're not introducing a variable to save as stdin and then proceed into the rest of the calculation. But I think for teaching this, I'm still going to deconstruct these functions as such. Okay, so now we're going to do get factorial.lean. This is a fun one. So here, so this is another way to do it. And so this is what my student Kevin came up with. You can define a function get input. And this is a get input has type IOString, okay? And it is simply set up to handle this part of that code that we've been discussing. And now when you need to do it, you can simply do get input arrow let num to get your number. But essentially, reminder, we have the factorial function. Ignore this factorial m for the moment. And let's look at our function call. So we have main, IO unit, do, we have a do block. And now we're going to start out with enter your number. I mean, hey, let's just try it. Let's just do lean dash dash run. I have get factorial. Okay, it needs me to put in a number. I put in 5 and it prints factorial 120. After you get the input and you store it as num, now it is a string. It is not a number. We can't do math on strings. We need to turn it into a number. So there is a string function. We were just talking about that. We have toNat, question mark. toNat will turn that into a thing. We also need to apply trim. Trim removes white space. So I think there's a new line character after this when I enter it, and it needs to trim that away. And so then that's how we have. We are going to then get my num trim toNat. And this either matches to some number or it matches to none. And if I put my cursor over the match, wait. Yep, if I put my cursor over the sum, you can see the word option in the syntax here. And how does option work? I forgot. I just did things a little bit out of order. I got too excited about get factorial. We have option.lean. Okay. To break down what is an option, this one simplifies how you understand options and how pattern matching is working in that case. Okay. Let's suppose I defined a function called safe divide. Safe divide is going to take a and b as natural numbers, and I'm going to option my nat coming out. If b is equal to 0, then my option nat is going to take a value of none. If otherwise, it is going to be sum A divided by B. And what that allows me to do is keep track of, is to manage error handling, basically. That's what option is for. Option is for error handling. So if I would be dividing by 0, I don't want to. And I want to avoid those things. And so that's what's happening here. Some is a valid thing. None is a type. Ooh, we can look at the type of none. It's an it is of type option alpha. And yeah, and honestly, go to check out those videos if you're curious about learning more about the depths of how monads work. Can be useful if you're going to write some of this error handling stuff yourself in order to understand how that's working. But for this scope, I just kind of wanted to show you something that works. And this is used to, again, it's a bit more of it's accommodating what people would like to write if they had an imperative programming perspective, but to do it within the realm of functional programming. So here is, again, my factorial function. If I have a number, then I'm going to let my factorial do a calculation on the number, and then I'm going to print my factorial out. If I don't have it, then I'm going to print invalid entry. Please enter a valid natural number. So I can try lean run get factorial again, and I could say, and we don't have anything. All right. I could do -1. This is an invalid natural number. I could do 1.0. This is an invalid natural number. This is a float. I mean, it has extra characters. It does not, the nat trim to nat, the num trim to nat did not succeed in turning this into a natural number. And so we enter into the none part of this pattern match, this branch. And that is really neat, I think, because what we've just done is we have successfully bridged I/O with pure functions that do math, that are guaranteed to always have solutions. And you can write proofs about those functions. But they're only going to be true. You're only confident. I mean, and the reason it works is because the IO monad and the options that we can build around it are essentially screening the messages before they get to the back kitchen. Essentially, like if the customer says, I would like you to bring me a wine that you don't have in stock, the waiter can, maybe they even go back and check or something, but like they're going to deal with it at this side by saying like, you want factorial of 1.0? I'm not going to give that to you. I'm going to give you a different kind of response. All right, and now it looks like we have 10 minutes. Ooh, two more slides. Okay. Compiling lean to C. Another little quick topic to cover. Here's just a simple line of code to turn lean into a C file. Lean --c equals, give the name of the C file that you want, and you give the name of the lean file that you want. And so I can do lean --c equals output.c. No, I'm going to call it C code. I think is what I called it. C code.c. And I can say get factorial.lean. And in my folder, you can say we have a C code. Okay, I called it C file earlier. They're the same thing now. Well, you open this up, and this is all code that's written in C. And this comes back, like if you want to use this for scientific computing, it means you need to be able to do calculations, and a lot of the time they need to be efficient. So many problems will even run supercomputers, and making your code run fast and efficiently is important. The developers of Lean foresaw this and built compilers that turn Lean into C code. This will also help you run. I mean, I don't necessarily need to install Lean on my supercomputer. I can install C. I can run the C code, but we actually have. I never quite figured out, and the people in my group never quite figured out how to get the compiler to work, because the very first include is some dependency package in here, which I don't have. I'm not really too worried about my C installation and having all those things, and so never quite got around this particular bug. But can we run C-related code like C++ or C# or even other languages? Good question, Urja. If you have specific questions about this, bring the conversation to Zulip, where people who have a lot more knowledge about this than I do can address this. There are ways to interface Lean with other programs, with other programming languages, but C is the one that it is mainly set up with if you're going to compile it to C. Most of the time, I think we just kind of want to run it on Lean code itself. There's been a lot of discussion of getting it to interface with Rust. Rust is a modern programming language that interfaces with C really well, and that's pretty nice. Rust also has a lot more type safety stuff like Lean does. It's not it can't do math proofs. Its typing system, it isn't as rich as Lean's is, but it does incorporate a lot of stuff that makes it very useful when people are writing. It's a lot easier to write Rust code than it is to write Lean code, is what I get the impression of, for example, when you're trying to write software, and you can still get some of these guarantees involved. And Simon is asking, does anyone know if the Lean 4 compiler is based on LLVM? I don't know the answer. I've seen chatting around it in Zulip. You can find those, I'm sure, by searching through the threads. People have talked about that. But I don't know enough about foundations of programming languages to address that one. Okay. And all right, I'm going to try to show us the CSV reader in the next few minutes, but if you're seeing my battery dipping low, this might terminate quickly. My charger is not going to reach the outlet from where I'm sitting. So we will see if we make it to the end. Okay, so you should have this CSV parser, and this is jumping far ahead. Okay. But this is taking a lot of what we've been seeing and just making it a lot more complicated. But this is what something more production ready looks like. This is Chris Lovett from Microsoft wrote this CSV parser. And so if you have tabular data and you want to use it, you can import it using a CSV parser. And so first of all, what is a CSV? CSV means comma separated values. And so every row has a number of fields, and you separate the values by commas. So data 1, data 2, data 3, 1, 2, 3, 1, 2, 3. This is a table of data, and you use commas to separate these. Variations on this exist. Sometimes they're separated by semicolons. Sometimes you end the row with this. Sometimes it has a header row. Sometimes it doesn't. But bottom line, that's what this format looks like. If you use Microsoft products, you can open up a spreadsheet. If it only has the data and nothing in it, then you can save it as a CSV file, and you can get one of these to work with. And here is the CSV reader. And bottom line, if you've used CSV readers from like other programs like Pandas and Python, import CSV really simply with a single line of code, they have lots of features and stuff. And basically, because this is a new programming language, you need to import those kinds of things yourself. And the documentation here illustrates, as Chris Lovett adding comments around different entries in the CSV, coming up with some terminology to do this. Needs to check if the character's Unicode value falls within certain ranges. Okay? Because you need to exclude things like a double quote, because a double quote is used to define a string, and you can't have double quotes in your code, essentially. And there's all these other types of circumstances, like I don't want to have a forward slash or some weird types of characters. Again, like most of this, most of these components and stuff are to deal with these exotic situations of what if someone puts a new line character inside of a string inside of a field of a CSV. Like that's kind of weird stuff, but it might happen. And the creator built in all these kinds of little exceptions and rules to handle those things, so that happens. And so on. And you can pass in a CSV file directly, and you can parse out an array from that, and so on. So at the very end of this, if you've downloaded this and you want to modify it for yourself, you will need to come into the read file and go into your own computer and give the absolute path to the file that you're trying to load. But this is my CSV from Excel that I have an example code from. And when I do, I changed the name of this. There I go again. Matrix, I took out, it's I need to go get the path for my string. Copy path. There we go. Okay. And so now when we eval this, we have loaded it into the memory as an array. And you can see we have the first row, data 1, data 2, data 3 as a list, or as an array inside of an array of arrays. So that's how we import this. And we note that I'm providing the absolute path to this. You can get the path of your current directory, by the way. This is just the, this is where the evals happen. We haven't had to deal with this because we're looking at that kind of code. So haven't had to deal with that yet, but now we're dealing with file input and output. So you can dig into these things too. We have the IO to do read files, and you can file content into this, and you can parse it and extract data from this, and then you can do math on the data, and you can do calculations, and that's all taking us toward this, the mechanics of doing what I described along the top row here, where you import data, then you do math on it, and you output data. That's how we do scientific computing. Once it's in, though, just like you saw with Lean, these are pure functions. And the stuff that's happening on the internal part of the code is going to be pure functions. We can write proofs about those. We can have confidence that those things are true. And in general, the design strategy of Lean is that as much as possible, you put things in pure functions inside that. I'll just say as like a final comment, since we have been talking about interfacing with other languages, there's, I'm going to bring up a slide from lecture 1. So this paper, Developing Bug-Free Machine Learning Systems with Formal Mathematics, 2017. They did, they did high-level math with Lean, and then the linear algebra to do the expensive computations that require lots of compute to do. They essentially had Lean call I believe it was a C library, which then did those calculations and got the results. But that's a possibility too. It takes a little bit of extra work. We haven't implemented that kind of stuff in our group yet. But that might be, depending on your application, might be actually really important in order to make your code performant or able to scale to reasonably complicated problems. If you do that, though, you can't trust that your linear algebra code is doing it correctly. You have to trust the library you're getting this from. If you built everything in Lean, then you could implement linear algebra and you could trust that Lean is doing it correctly.